Okay, so in this video we're going to calculate the potential above the end of a short rod. You have an image here that you can use, and I strongly encourage you to pause the video and try this yourself before you see the solution. Decide on your approach. Is this going to be Gauss's law or a Coulomb's law kind of approach? Is this a Gaussian or non-Gaussian symmetry? So I'll see you back in a moment. Okay, so the first thing to take note of is that this is a non-ideal Gaussian symmetry, so it's not ideal Gaussian, and as a result we're going to take the Coulomb's law approach. So we start with dV is equal to k dq over r, or V is equal to the integral of k dq over r, and our limits of integration, now we're going to be summing up along the x-axis here. So we're going to be going from, got to set an origin, so we'll say that x equals 0 right here, and down here x is equal to L. And so our limits of integration will go from 0 to L. Now when we look at dq, we know that dq is going to be equal to lambda dx, and that r, now this one's going to be a little more difficult, r is going to be equal to the square root of x squared plus y squared, where y is a constant value. This value never changes, and so y is equal to h in this problem because it's a constant. Okay, so y is equal to h. So substituting this back in, we get v is equal to the integral from 0 to L of k lambda dx over the square root of x squared plus h squared. Okay, so k is constant, lambda is constant, h is constant, but we can't take it out of the square root, so we're going to have to leave that in there. And so we're going to get v, the potential is equal to lambda over 4 pi epsilon naught times the integral from 0 to L of dx over the square root of x squared plus h squared. Now, what you're going to have to do is either solve this integral longhand, or you're going to have to look it up in an integration table, and if your calculator has a computer algebra system on it or a CAS, then you can use that to get the value of that integral. Don't forget also that we're going to be taking lambda, and we're going to write that as Q over L in just a minute. Okay, so this is going to be equal to Q over 4 pi epsilon naught L times the natural log of x plus the square root of x squared plus h squared, and this is evaluated from 0 to L. Alright, so finally what we get is the potential is equal to Q over 4 pi epsilon naught L times the natural log of, now we can write this as a fraction, and so we're going to get L plus the square root of L squared plus h squared divided by h. Okay, now how do we get that h? Well, if we look at this over here, we have we'll just look at what's inside the natural log. So we get x plus the square root of x squared plus h squared, and x is 0 at our lower limit, which is the bottom of our radical here, or not our radical, the bottom of our natural log. And so x here becomes 0, this x becomes 0, and we're left with the square root of h squared, which is just equal to h. And so this is going to be our final answer for this particular problem.